5 carbon ring. So I'm gonna say, this way. 1, 2, 3, 4, 5. So this part is cyclopentane, right? You all can see it. And then you have the hydrogen on this carbon, and then you have the methyl group attached to that, right? So now we are focusing on this carbon over here, this one. So you have hydrogen, methyl group, and then you have 2 carbon in the ring, right? So this is the carbon you're gonna focus on, okay? So now, when you see this symmetry, it is a little bit tricky whether you're gonna take the methyl group like that, okay? So in the same plane with this one, this hydrogen, so I'm gonna make it this hydrogen and this hydrogen on the same plane like that. Okay, so one way is to do that. Other is, let me make like that, just like a Twitter database, in which you're gonna have 2 hydrogens on either side of the plane of this one. Okay, so it can have the free rotation around the carbon-carbon bond. So you can put any way you like, right? Now the question is, when you see the symmetry, which conformations we gonna take out of this, right? So remember the ethane or butane energy profile you had before. So depending on the rotation you have, you're gonna have the low or high energy, depending on whether you're gonna have these hydrogens very close, so that you're gonna have the crowding like eclipse conformation, or whether you're gonna have this hydrogen away from other hydrogen, nearby hydrogen, so you're gonna have the staggered light conformation and you're gonna have the low energy, right? So always you're gonna choose the lowest energy conformation possible, okay? So in which case, so to be far from this one, so what you're gonna do is something like this. So when you do this hydrogen is gonna be away from these 2 hydrogens, okay? So if you do like something like this one, so now these 2 hydrogens gonna be closer, you're gonna have the higher energy, right? So you don't take that. So you're gonna take something like this one, so that these 2 gonna be in one plane, they are farther, they are orienting in different direction, they are farther, and then you are not close to these hydrogens, so gonna be in between these 2 hydrogens, okay? That's gonna be the lowest energy possible, okay? So now when you have this, what you're gonna do is you're gonna cut right through over here, right? So when you cut that, in one half, what are you gonna have? You're gonna have this part of the ring, 1 hydrogen of the methyl, and then a half of that hydrogen, okay? And then in the other side, you're gonna have the same thing. You're gonna have the half of this hydrogen, you're gonna have 1 hydrogen, and then you're gonna have the half part. So you're gonna have exactly identical parts, halves, right? So that's the reason why you have the symmetry there, okay? So now, why you don't have the 4 different groups attached to this carbon? So you have the unique hydrogen, of course. You have methyl, so these 2 are different. So now the question is, what about this and this? So you have the same carbon, same type carbon on either side, right? So you have tie over here. So see if you can break the tie, okay? I'm gonna go to next carbon. You have the same type carbon over here like this one. So you don't have any difference there, right? If you have, say, oxygen over here, then yes, this carbon gonna be chiral. You're gonna have the 4 different, even if you have tie over here, oxygen gonna break the tie, you have oxygen in one side, you have the carbon in the other side, so when you cut through it, you're gonna have 4 different groups attached to the carbon. right? In this case, you don't have symmetry at all, right? So in one half you're going to have oxygen, other half you don't have oxygen, you don't have any symmetry there, okay? So that's where you're going to see. So when you visualize the molecule, you're going to visualize in 3D and also the lowest possible conformation you're going to have. Right? So now, clear? Good? Alright. Alright. So then we're going to continue. So chiral, achiral, you know that, right? So now we're going to name different terms like enantiomer, diastereomer for the isomers of these type of molecule. So for this, you have to know one thing before that, okay? So the mirror image. So now, whenever the molecule is given, you're gonna visualize the image of that when you put in front of the mirror, okay? Let's say this one is an example, the simple one, okay? So I'm gonna take this molecule and then I'm gonna put the mirror over here and then I'm gonna see the image of this molecule in the mirror, okay? So when I do that, what type of image you're gonna see? So I'm gonna take the molecule. If you see the image of that, so the near the object you're gonna have to the mirror, you're gonna see closer in the image. Okay? So the farther the atom you have, you're gonna see the farther position in the image. Okay? So that's how you're gonna see the image in the mirror. So now I'm gonna put this, the green color group, on the farther side. Because in the image I'm gonna see farther away. Okay? So that's where how we're gonna do is something like this. So this is gonna be the image. So the hydrogen is on the top. And then you have the blue and the red. They're gonna be closer to the object. Right? So in image you're gonna see these two closer. And then the green one you have, that green gonna be the farther away. So that's going to be the image of this molecule when you see through the mirror. Okay? So any question up to that point? To view the image. So you're going to take the molecule and then you're going to see the 3D image, again not 2D, 3D image in the mirror. Okay? So whenever you draw that, you're going to draw something like this. Right? So now you can use this like a bold face line and then the dotted line to represent that, right? So I'm gonna do something like this one. So let's say green and white. These are in one plane, okay? And then from your side, I'm gonna draw the red one as the bold line. That's towards the viewer, okay? And then the blue one, you're going to write the dotted line. Right? So that's the way you're going to draw in 3D. So now, how are you going to distinguish the isomer is you have the image, you have the molecule. Now, can you superimpose that into this molecule? So this is different than this one. Okay, so if I try to superimpose, so remember this is image, this is the molecule, okay, so if I try to superimpose say hydrogen and then say the red one, so other two do not coincide, right? So you can do two like that, but blue and green, they are different, right? So you can do many different ways. Let's say try to do with the green and the blue. So now you have the white and red, they don't coincide, right? So you can do say red and then white, for example. Okay, I'm gonna do like that way. So again, doesn't match. That means these two are different molecules. Okay, so what is the difference? It is like I just switch one group to the other side. So these two are going to have different position in space in these two molecules, right? So whenever you have this situation, it is called the non-superimposable mirror image. Okay, so you have the image, every object gonna have the image, right? But it's gonna be non-superimposable. You cannot coincide all the groups in one point, right? So whenever you have that, you're gonna have the chiral molecule. That's the property of that, right? Let's do the same thing for the achiral molecule. Okay? So this is going to be something like this, right? So do you know the difference between chiral and achiral?
A chiral is where you can superimpose it onto its mirror image, and then chiral is where it's basically like you can try to, but it's never going to match exactly.
Yes, that's right, but very simpler than that.
The achiral has the 4 bonds, but they are not bonded to the
Exactly, right? So chiral, so the simplest way of saying that, even going before the mirror image, okay? So take the carbon, see what type of groups you have there, they're all 4, right? So this carbon is chiral. Very simple, okay? So this one, this is also chiral, right? Correct me if I'm wrong. This carbon is also chiral because you have 2 same groups and then you have 2 different ones.
That's
It
not
is
chiral.
This is all chiral. Okay? That's the simple thing. If you have at least 2 same groups attached over there, 2 or 3 or 4, doesn't matter how many you have same. If you have at least 2 same groups, this carbon is all chiral. So to be chiral, you must have all 4 different groups attached to the carbon. Okay, that's the simple distinction. Okay, so now let's see all chiral. So here, the difference you're going to see is this. You're going to have the image. So every object going to have the image, right? If it is all chiral, you're going to have the superimposable image. If you have the chiral carbon, it's going to have the non-superimposable image. That's the difference, okay? So now, let's see why it is superimposable, okay? Let me take the molecule like this. I'm going to put the mirror over here. And then what's going to be the image? So image is going to be something like this. So you have the red on the top, you have the 2 hydrogen closer to the mirror, you're going to have closer for these 2 hydrogen, right, in the image, and then you're going to have the blue farther away. So that's going to be the image of this molecule, right? So now, when I do that, I can rotate a little bit like that. So, are these groups are superimposable to each other? Yes. You can have the red together, a blue together, hydrogen together. So you cannot distinguish this with this, the same molecule, right? So you have the image of that, but this image is not different than this. They are the same molecule. Okay? That is superimposable. So you can put all groups you have in the carbon in one point, like hydrogen, and then blue, red. You have all similar, right, or same. You cannot distinguish that. So this is called the superimposable mirror image. Okay? So now, once you are very clear with this, now for the enantiomer, you're going to focus this one. it must have the chiral carbon, and then the image you have for that molecule gonna be non-superimposable. Yeah.
So that example that chlorhexidine, that is superimposable because it has two carbons attached to it?
1, 2, 3, no. All right, so now the question is, okay, you have example over here, right? This molecule. So you have 1, 2, 3, 4, 5. So which carbon is going to be chiral? Can you point it out?
The third one?
So this carbon is going to be the chiral carbon. Okay? So why it is chiral? You're going to have the hydrogen over here. You're going to have the, say, chlorine over there, right? And then you're going to have the ethyl group over here. This is C2H5. A put in one word. And then what is on the other side? Propyl. It's not ethyl, right? C3H7. Okay? So you have all 4 different groups there. The other way of saying that is you have the tie on the next carbon for both. To break the tie, you're going to go further than that. So second neighbor, you have the tie after that. What about the third one? So you have the carbon in one side, you don't have carbon on the other side. They are going to break the tie. So you have 4 different groups. You have the chiral. Now what's going to be the image of that? So if you keep as is, then image is going to be the right one. This is going to be image of the first molecule. So you have the, so if you put the mirror over here, so you're going to put mirror like that. Okay. So in the mirror, so you're going to have the 2 carbon atom towards mirror, right? So in the image, you're going to see that first. So that's the reason why you have 2 carbons over here, the image, closer to the mirror, right? And then you have the 3 carbon or the propyl farther away from the chiral carbon. So you're going to see the same thing in the image. So these 3 are farther away from the chiral carbon. So the molecule on the right side is the image of the first side, on the left side. Then now if you try to superimpose image into the molecule, it's going to be like this. You can never superimpose all 4 groups there, right? So this is called enantiomer. Okay? So that's the name for that. This is called enantiomer. Again, this is the name for that. So now you can define the enantiomer. See the requirement. So the carbon center must be chiral. If you don't have chiral, there is no enantiomer at all. Okay? If you have that, you're going to have the image of the molecule, which will be non-superimposable, of course, right? So the pair, so enantiomers are the pair. So the molecule and the image. So that pair is called enantiomers. Okay, so here as an example, this is the molecule you have. So you're going to have the image of that. This is the image, right? So these 2, one pair is the enantiomers. Okay? So that's how you're going to define. So now, in your book, like the 180-degree flip, pancake flip, something like that, this is just the different way of saying that. So you can use that like that if you feel comfortable, or just by taking the image directly. So the same thing, doesn't matter. Okay. So if you see the image, you can rotate the other side 180 degree, and then you're gonna have the distinction. So if you see over here, in the molecule, you have the chlorine on the front side, right? But if you see the image over here, it is on the front side, right? So it is like saying this way. So I have this is on the front side from your side, right? Image is still going to be on the front side from your side. Okay? So that's how you're going to define enantiomer. Any question on that?
So then there are reactions that allow us to switch the molecule between the left and right-handed version of the enantiomer?
Of course. Yeah, so many different reactions. So for this one, we're gonna see we don't go through all the reactions here. So the properties, it has a specific property, it's gonna rotate the plane of the light. So that's the one we're gonna focus over here. So you have the different rotation angle between these two molecules. Okay, so that's the one we're gonna focus. But you need to go that far. Okay? Good? Alright. So now you can define the enantiomer, right? So let's see one more example. So this is the molecule, say. So isomer A is a given molecule, you can call that. So molecule. And then isomer B is image. You can take that away. Okay? So now, if you compare these two, so which is going to be the chiral carbon? So you can have this one, chiral carbon, because you have the hydrogen over there, right? You can take a hydrogen like this. So now for the image, this is going to be the image, right? So the other one, you can have the chiral carbon, this one as an example, and then you can have the image over here, right? So sometimes you can have more than one chiral center in the molecule. Doesn't mean that you can have only one chiral center. You can have many, 2, 3, so more chiral center you're gonna have. You're gonna have more number of isomers there. Okay, we're gonna see more example when you deal with the diastereomer later. But before we go there, we're gonna name the isomer now. Okay, so now the question is, let's say these two again. So the simple example, if you wanna name this molecule, so what's gonna be the name? So one carbon, you're gonna have the methane. Okay? So let's say this is chlorine, this is iodine, this is bromine, right? This is hydrogen. So what do you call it that? So if you have the one chlorine, you're gonna call chloromethane. If you have one bromine, you're gonna be bromomethane, right? So you have the iodo, you have the bromo, you have the chloro, and then you have the methane. Right? That's the name. Okay? So now what about for this one? So you don't have different name, so you have the same thing, right? So you have the one chloro, one bromo, one iodo, and then methane. Right? So in terms of name, you don't have any difference over here. You have the one iodine each, one bromine each, right? One chlorine each. So you can have the same name of this if you follow the IUPAC rule. Okay? So now the question is how to distinguish that. So you have different molecules, they have different property. So how to distinguish in terms of the name of these two molecules. Okay? So that's the one you're gonna give different name. Okay? So we have some rule to follow that. So we're gonna name one name for this and then the other name for this. So you're gonna distinguish these two molecules. Alright? So how are you gonna do it? So the name is called CIP. So name of the scientist over here. So 3 propose the rule, and then we're gonna follow that. This is called CIP rule. Okay? So how you're gonna do is you're gonna see the 4 different substituents on the chiral carbon, and then you're gonna number these 4 based on some criteria, and then we're gonna assign either R or S. So you're gonna say R, name of the molecule, and then S, name of the molecule. That's how you're gonna distinguish that. Okay? So now, to make it easier, R you can take as a clockwise. When you go through the numbers, you give them. And then the S gonna be the counterclockwise for the number you give them. Okay, so let's see the rule one by one, so it's gonna be more clear. Okay. So now the question is how to number them, right? So number 1 says that you're gonna number the 4 different atoms attached to the chiral carbon with the priority rule in terms of the atomic number. Alright, so you don't need to memorize anything. Atomic number you can see in the periodic table. So you can see which atom is going to have the higher atomic number, right? So you see in the table. So as an example, let's say this one. Okay? So this is chiral carbon. I have 4 different atoms attached to that. Okay? So iodine, bromine, chlorine, and hydrogen. So now I'm going to go to periodic table, and then I'm going to see the atomic numbers of hydrogen, iodine, chlorine, bromine. So which one out of these 4 groups, you don't take the chiral carbon, that's the central piece, so you're going to see for the 4 attached to that. Okay? So out of these 4, that is hydrogen, chlorine, bromine, iodine. So which one going to have the highest atomic number? So if you go down the column, you're going to have more atomic number, right? So the one you have on the top going to have the lower one. So iodine is going to be on the farther down in the column. Iodine is going to have the highest atomic number. So I'm going to say number 1 for that, iodine. Okay? What next? Chlorine or bromine? Bromine. So number 2 is going to be for that. And then chlorine is going to be next lower, right? So number 3 is going to be for that. And then these are the list. Number 4 is going to be for that. That's how you're going to number it. Okay? So the highest atomic number, number 1. Lower than that, number 2. Lower than that, number 3. Lowest one, number 4. Okay? So that's how you're going to number, right? So let's see over here. So this is the one I showed you. So iodine number 1, bromine number 2, and then chlorine number 3, hydrogen number 4. Okay, so this is like this molecule. So now let's see the second one. So you're going to take the chiral carbon, which is this one over here. Okay. So now you have chlorine, oxygen, nitrogen, hydrogen. So which one going to have the highest one? Chlorine. So number 1 for that. Oxygen going to be next, number 2, right? And then nitrogen, number 3. Hydrogen, number 4. So that's how you're going to name it, right? So another example, like this one. So deuterium is like one more than hydrogen, right? So second lowest is going to be deuterium. So lowest is going to be hydrogen, and then chlorine number 1, oxygen number 2, right? So number 1, number 2, number 3, number 4. Right? So that's how you're going to name it. So now here, what if you have the tie? Sometimes you can have tie. Okay? So you're going to go farther away until you can break the tie. Right? Say the last example over here. So let's do for this one. So this is the chiral carbon you have. So hydrogen obviously going to be the lowest one. And then you have the OH group over there. So oxygen going to have the highest one. Why? You have the carbon and carbon as 2 groups over there. Okay? So first oxygen is highest. Because oxygen going to have higher than carbon. There is no confusion on that, right? So you put number 1 on oxygen. So now carbon is going to be number 2. Okay? So now the question is, which carbon is number 2? You have carbon in 2 sides, right? So let me see, let me color with different color. So either the red color carbon or the purple color carbon, okay? So now the question is, whether you're going to put number 2 for the red color carbon or number 2 for the purple color carbon. You have tie over there, right? So now you're going to go further away to break the tie. So, wait. So you're going to go next, which is oxygen over here. Next, you have carbon on the other side. Now you're going to break the tie. So which carbon is going to have number 2? The carbon bonded to oxygen. Right? So I'm going to put number 2 for that, number 3 for that, and then number 4 for the hydrogen. That's how we're going to do. Right? So sometimes we have tie. You're going to go next neighbor for that tie atom, and then next than that as needed until it's gonna break the tie. Okay? Yep.
So the reason why we have the purple carbon labeled 2 is because when you look further, oxygen weighs more
Then carbon.
Okay.
Yep. So you're gonna go further away until you find one higher atomic number and the other lower atomic number. Okay, so that's how you're gonna break the tie. If you have this scenario. Okay. So the other example, the same over here. So this is the chiral carbon you have. So you have the same atomic number for carbon pointed by arrow. You have the same for the next one. You have the same for the third neighbor. You don't have difference on that. Up to 4th, you have the same, right? So now, after the 4th neighbor, now it breaks the tie, right? You have carbon over here, and you have the hydrogen over there. So carbon is going to have more atomic number than hydrogen. So you're going to put number 2 for that over here. And then you're going to have number 3 over here. Okay? So that's how you're going to break the tie. Right? So now you know how to number it. So you know the priority. So now, sometimes, if you have the double bond as a neighbor, okay, so you don't take the directly double bonded carbon because you must have 4 bonds on that. If you have the double bond as the neighbor to break the tie, okay, you can count as 2 atoms on that. Okay, so if you have the double like this, you can think like a 2 carbon-carbon bonds like that. Okay, so they're going to break the tie. Okay. So now, let's put all together. Okay, so you know how to number it? You're going to put 1, 2, 3, 4. So now how to name R and S. We based on that. Okay? So again, let me show you this one. So this was the first example, right? Remember, you had 1, and then you had 2 for bromine, and then you had 3 for chlorine, you have 4 for hydrogen, right? That's the number we have. So now, what you're going to do is, when you view from your side, always put the lowest priority atom, that is the number 4, that has the lowest atomic number. You're going to put that on the back, always. Okay, so you are viewing this, you're going to point hydrogen away from you to the back. So now the 3 groups are pointing towards you. Okay, so now see the number. You have 1, you have 2, you have 3. Okay, so which direction are you going to go? So 1, 2, 3.
Right.
Is it clockwise or the counter?
Clockwise.
That's why it is R.
Mm.
Okay, so if you go to the clockwise, 1, 2, 3, you're gonna name this R molecule. Okay, so now let me show you the image. So this was image of that, right? So now the image is gonna have the different than that. Okay, let me do the same thing. I'm gonna point the hydrogen on the back. So now you have the number 1 for iodine, same as this one. Number 2 for the bromine, same as this one. Number 3 for the chlorine, right? So now see in which direction you're gonna go, counter or clockwise for this, for the image. Counter. So this is S, right? So for the pair, whenever you have the enantiomer pair, one gonna have R, other gonna have S. That's how you're gonna distinguish them. So now you have different name. You have the R and then name of the molecule for this one. You have S and name of the molecule for this one. So now they are different. Okay? That's how you're gonna do it. All clear? All right. Then, so the second method, you're gonna make a little bit more confusion. So you're gonna go through that. You're gonna read it. Or follow this one. It's gonna be easier. Okay. All right. So now, let's see the properties of these molecules. Okay. So now we know enantiomers, right? So we know how to name them. So we can name this. Now, what are going to be the properties of this? So the property we're going to focus is the interaction with the light. Okay. So now, if you recall your Gen Chem class, so in which direction the photons travel? So you have the light wave, or you can say the electromagnetic radiation, like something like that, right? So like that. So let me write with a different color. You had one figure like something like this one. So electromagnetic radiation. So one, you're gonna have the one direction, and the other gonna have to the other direction. So electric and magnetic component gonna be perpendicular to each other, and you're gonna have the light in all possible directions, right? So if you take the sample of light coming from the sun, and then if you analyze that, you're gonna see in all possible directions. Okay, so to make simple, what you're gonna do is you're gonna do the plane polarized light. We're gonna take this light. So what is that? This is one portion from the sample you have. Okay, so you're gonna make this slit, and then you're gonna just make a hole in one direction, and then you're gonna allow the sample to pass through that. So for the other possible direction, the light gonna be absorbed by the slit, and then only one direction you have gonna be passed through the small hole, right? So this is called the plane polarized light. So with only a given direction along X or Y or Z, whatever you want. So you're gonna take the light in only certain direction. This is called the plane polarized light. Okay. Now, when you have that light, then what you're gonna do is you're gonna pass that plane polarized light through the sample of this thing. Okay? So you have the sample in a beaker or cuvette, whatever you have, and then you're gonna pass that light through the sample. Okay? And then you're gonna measure the angle again when you have the light out from the sample. And then you're gonna compare the angle. So what was the angle before the light was passed? And then what was the angle after it passes through the sample? Okay, so if you see that, you're gonna see this. You're gonna see the rotation of the plane of the light by certain angle. So how much angle? It depends what molecule you have. So some gonna rotate with the larger angle, some with a few angle, right? So it depends on the type of molecule you have, but they're gonna rotate the light, plane of light. Okay? So whatever the molecule they're gonna rotate, this is called the optically active. So that's the name for that. That is for enantiomer in particular. Okay? So if you have the enantiomer, that's gonna rotate the light, that is the optically active. So if it is not enantiomer, let's say like this is not enantiomer, you don't have all four different groups there. So this is optically inactive. So it doesn't have R and S conformation, so it doesn't rotate that. So these molecules gonna be inactive. Okay? So enantiomer gonna rotate the light. These are optically active. Okay? So now question is, in which direction it's gonna rotate? To the right, to the left? It depends which enantiomer pair you have over there. If you have R, it can rotate in one direction. S, it can rotate to the other direction. Okay, so again, always R and S gonna rotate in different directions. Okay, but if you have inactive like this, these are not enantiomer. You don't have R or S for this one, right? So because you don't have the non-superimposable mirror image for that. This is not enantiomer. Okay? So here again, this is the molecule 2-bromobutane, right? So this is R. So why it is R? You're gonna do the same thing. So to check it, it is the theoretical concept again. So you're gonna do the same thing. So you're gonna number all the atoms bonded to the chiral carbon, and then the number 4 you're gonna point to the back, and then you're gonna have 3 groups over there, and then see whether you're gonna go clockwise or counterclockwise. Right? So this is gonna go to clockwise, so you have R for that. Okay? So you're gonna have the S also. So if you take the image of the first molecule, like this is the image for this one, right? So the image is going to be S. Okay, so that's the reason why you have S over here. So now, when you see the rotation, so this one, the molecule, is going to rotate to the left, R going to rotate to the left, and then the other one, you're going to rotate to the right. So see the different direction? So the point over here is don't take as R gonna rotate to the left, S gonna rotate to the right. No. It could be, not always. Okay? So the rotation is the experimental quantity. Until you pass through the sample and then see the rotation, you cannot guess in which direction it's gonna rotate. Okay? Sometimes R molecule can rotate to the left, sometimes to the right. So the rotation is the experimental quantity. Okay? But R and S, these two are the theoretical quantity. So you can say whether it is R or S just by looking the molecule. Right? So you're going to take the molecule, you're going to do this, and you're going to see whether you're going to go to the clockwise, counterclockwise. So this is theoretical. Okay? So you see the molecule, and then you're going to name R or S. But the rotation is not theoretical. Okay? This is from the experiment. So we're going to do the experiment and then we're going to assign the rotation value 20 degree or 25 degree or 15 degree like that. This is from the experiment. Okay? So now, so let's see. Let me explain this one and then I'm going to go back. Okay? So now you have so many different notations. So one gonna be D or L. So D is a dextro-rotatory, L is levo-rotatory, and then you're gonna have plus and you're gonna have minus. So D or plus is the same thing. And then L or minus is the same thing. Okay, so these are the direction of light rotation. Okay, so don't be confused with DL and then RS. They are different things. Okay, so R and S gonna be for the enantiomer pair to name that, and D and L is for the rotation of the light. So whether you're going to rotate to the right or to the left, you're going to call D or L, right? So this D is going to rotate to the right, that is the clockwise, and then the L going to rotate to the left, that is counterclockwise. Okay? So the rotation for the clockwise is going to be plus, counterclockwise is going to be minus. Okay? So again, these are experimental. Don't be confused with that. Right? So whenever you have the plus minus DL rotation, that's from the experiment. That's the rotation of light by the molecule. Okay? Alright. I think we're going to start over here. So this is a little bit confusing, so make sure you review that.